Okay, so let's get into an example. So this first example here, we have a function. It's and you should hopefully recognize this kind of function. It's a rational function. We talked about these in semester 1. More specifically, it's a linear over quadratic rational function. And I'm asking that you don't use a GDC for this. What we're going to be doing is we're going to be, number 1, finding and classifying the stationary points. When it says classify, what it means here is tell me if the stationary point is a local max, local min, or stationary point of inflection. Okay, so to find and classify the stationary points, what we're going to need to do is first find the derivative. And we're going to need to set the derivative equal to 0. After all, that's what it means for a point to be a stationary point. So let's first find the derivative. Here we notice that we have a ratio of 2 functions, so we're going to have to use quotient rule. So quotient rule says, take the derivative of the top. Okay, so we're going to take the derivative of the top. Derivative of the top is just 1 times the denominator. Denominator is x squared plus 1, so I'm just going to write that as 1 times x squared plus 1. Take away the top. Okay, so the function at the top is x times derivative of the bottom. The bottom's derivative is 2x. So we're going to have take away x times 2x. And then don't forget we need to divide by this denominator squared. So like that. Now if you simplify this, 1 times x squared plus 1, that's just x squared plus 1, take away, and then 2x times x is 2x squared. So we're going to have 1x squared take away 2x squared. It's going to be negative x squared. And we're also going to have a 1 left over. So we're going to have 1 minus x squared. You can just confirm that that is the right simplification. Now, even though we do want to set the derivative equal to 0, and I guess if we're finding stationary points, you can do that right away, like you can set the derivative equal to 0. We also care about where the derivative is positive and negative. And the reason that is because the word classify is used here. So we don't just have to find the derivative, stationary points. If we just had to find the stationary points, you could just set the derivative equal to 0, locate the stationary points, you're done. But because it's asking you to classify, they want to know, are the stationary points local maxes, local mins, stationary inflections, which is it? So because of that, we're going to need a sign chart. And because of that, we're going to also need to factorize. So I'm going to factorize the numerator here. The numerator is 1 minus x squared. So if we factorize, we get 1 minus x times 1 plus x, all divided by x squared plus 1, all squared. Okay, so let's now find the stationary points and classify them. By the way, part B will be to sketch the graph, and I think I'm actually going to move this down a bit so we have a little bit more space. What I'm going to say is stationary points exist when f prime of x is equal to 0. So what I'm doing here is I'm setting the derivative equal to 0, and if I do that, I get this. 0 equals 1 minus x times 1 plus x. Now here, we don't really care about the denominator. If the derivative is equal to 0, that's going to be when the numerator is 0. Also notice something, and this is something I forgot to mention earlier, but the denominator is always positive. This thing is always positive. And we'll come back to that later, but that's an important fact to recognize. This is a parabola, the typical x squared, but shifted up 1 unit. Because this shifted up 1 unit, it has no x-intercepts and it opens up, so it's always positive. Okay, so the derivative will be 0 when the numerator is 0. The numerator is 0 when x is equal to plus minus 1. Now, this is not a stationary point. A lot of people make this mistake. They'll say, oh, this is the stationary point, but really these are the x coordinates of the stationary point. So when you're finding stationary points, really what they want you to do is find an xy pair. So find the coordinates. So let's do that. When x is equal to 1, we need to figure out what the y values are. Now here, a lot of people will accidentally plug this into the derivative. what you want to do is find the stationary points lie on the original function. So you want to evaluate the original function when x is 1. So if we plug in 1 into the numerator, we get 1. In the denominator, we get 1 squared plus 1. It's going to be 2. So y is going to be 1/2. And then similarly, when we plug in -1, so if we plug in -1 into here, in the numerator we get -1. In the denominator we get 2. So overall we get -1/2. So I'll write that down. When x is equal to -1, y is equal to -1/2. Okay, so I'm pretty happy with all that. We have our stationary points, so these are our stationary points. The issue is we haven't classified them, meaning we haven't told the reader, hey, are these local maxes, mins, or inflection points? For that, we're going to make a sign chart. Okay, so this is very similar to what we did last time. We're going to make a sign chart, put in -1, +1. At -1, the derivative has a value of 0. At +1, the derivative has a value of 0. And then what we need to do is figure out what the sign of the derivative is around those stationary points. Okay, so here what we're going to do is we're just going to plug in a number to the left of -1, maybe like -2, see what happens. If we plug in -2 here into this factor, we get a positive, and then here negative. Overall, we're going to get a negative. Now, I didn't even consider this one. And this is an important skill to have. You need to be able to quickly recognize when something is always positive. We know that x squared plus 1 is always positive. It has no x-intercepts. The parabola has no x-intercepts, and it opens up. And so x squared plus 1 all squared is also always positive. So you don't even have to consider this. You just look at the numerator and look at the signs of the numerator. Okay, so now we have to test the value between -1 and 1. We could test 0. If we test 0, we get positive, overall positive. And then if we try a value to the right of 1, we're going to get a, like maybe 2 or something. We'll get negative and positive, so negative overall. Okay, so what this tells us is that the function is decreasing, then increasing, and then decreasing. And that also tells us that at -1, maybe I'll do this in a different color. So at x equals -1, you can see that the function is changing. The function is going from decreasing to increasing. So that means that we have a local minimum. And then in the same way, at x equals 1, the function is going from increasing to decreasing. So we have a local maximum. Okay, and this is the classification step, but you have to write it down for the reader. So for the reader, we have to state like, hey, this is my local maximum. This is my local minimum. So I'm going to do that now. So I'm going to say, therefore, and this is my final answer, -1, -1/2 is a local minimum, local min. And then also 1, 1/2 is a local maximum. And this is your final answer. I'll put this one in a box. This is the final answer to the question. The question's asking you to find the stationary points and also classify them. So we've done that now. Okay, so the process defining and classifying stationary points, again, find the derivative, set the derivative to 0 to find the stationary points, but then also make a sign chart and look at the sign changes of the derivative to classify the stationary points. And hopefully that is clear. Part B is going to ask us to sketch this function. Before we sketch this function, I want to leverage symmetry. Remember, one of the sketching tips I gave you earlier was consider any symmetry that the function has. So here, if you take a look at this function, it may not jump out to you right away, but after I show you, if you plug in the opposite input, so f of -x, you'll notice the top just turns into -x, and the denominator is -x all squared plus 1. And you can simplify the denominator. -x all squared is just x squared. And so the denominator remains unchanged. It's x squared plus 1. The numerator is the opposite of the numerator here. Okay, so this is the opposite. And so overall, you get f of -x is negative negative f of x. And this is an example of odd symmetry. So this function has odd or rotational symmetry. I want to point this out to you before we sketch, because the fact that it's odd symmetry, it really helps us with our sketch, because it tells us that the function should have rotational symmetry around the origin, and you can use that. So this is concept of symmetry is very important. Whenever you can use it, it'll help you more easily sketch. Okay, so let's do a sketch. Now, what I want you to do is, when you sketch your graphs, okay, I want you to try and sketch them so that the x-axis kind of lines up with the x-axis of your sign chart. Or I should say, the x equals -1 here lines up here, and then this x equals 1 will line up here on your graph. In between, we're going to have our y-axis, okay? But it's nice to line it up, because when you line it up, I'm just going to move this down. When you line it up, it's easy to see where the function is increasing and decreasing. Okay, so we know, for example, to the left of -1, the function is decreasing, so it's going to be decreasing. And then between -1 and 1, it should be increasing. And then after 1, it should be decreasing. Okay, now the other thing I said was, if you can, use intercepts. Intercepts will help give you more points where the function has to pass through. Here, we can find the y-intercept by setting x to 0. So when x is 0, we can go back to the original function. When x is 0, the numerator is 0 and the denominator is 1. So the y value is 0 when x is 0. So the y value is also 0. That tells us that we have to pass through the origin. So I'll put that point in there. We also have two other points. We have -1/2, comma -1, comma -1/2. So -1, comma -1/2, I'll just make that here. So I'm choosing this to be -1/2. And then we also have 1, comma 1/2. So 1, comma 1/2, I'll choose that to be, I'll choose that to be here. Okay. This is maybe a little bit confusing. That's a 1 here. Okay, so we have these 3 points. This might not help, but we have something. We have 3 points that we have to pass through, and we also have the fact that the function should be increasing. So between these 3 points. Right here, the function should be increasing because the derivative is positive. Now on this side, the function has to be decreasing. So, on this side, the function needs to be dropping. But we're just not sure what the end behavior here looks like. So, is it dropping from here? Is it dropping from here? How is it dropping? And then here on this side, it's dropping as well. But, where does it drop to? And this is where end behavior kind of helps. You need to be able to evaluate the end behavior of a function, at least for common functions that we've talked about so far. As we get into grade 12, you'll be able to evaluate more and more complicated end behaviors. But for this one, we have talked about the end behaviors of these kinds of functions. This is an example of a linear divided by quadratic function. And so as x gets very, very, very large, maybe positive infinity, the linear function on the numerator is going to grow much, much, much slower than the quadratic function in the denominator. So because of that, the ratio is going to go to 0 as x gets very, very large. And so I'll just make a note of that. Okay, so I'll just make a note of this. As x goes to positive infinity, the y values seem to be going to 0. And actually, as x goes to negative infinity, the y values will also be going to 0. Now, we don't really care so much about which side they go to 0 on, because we can actually figure that out from the sign chart here. So we know that the values after x equals 1, the function values have to drop off. So they have to go down, and they have to approach 0 because it's a linear over quadratic function. So we know that overall it's doing something like that. And then similarly on the other side, we know that the function values are decreasing to the left of -1. So we know it needs to be decreasing. We also know that the end behavior is they're going to 0. The y values are going to 0. So overall, the function values do something like that.